Hello there and welcome to the Sleepy Orbit channel. I'm so glad you found your way here tonight because we're about to begin a gentle, immersive journey through some of the most awe-inspiring truths the universe has ever revealed. Wherever you are in the world, curled beneath soft blankets, gazing out at a sky scattered with stars, or simply resting your eyes after a long and weary day, please allow yourself to settle into this shared moment of stillness. Let the clamor of the outside world soften into silence, and let your thoughts grow quiet, like distant starlight fading into the deep velvet hush of night. Now imagine yourself drifting, weightless, through the endless ocean of space, gliding silently past hidden worlds cloaked in mystery, past luminous stars burning with ancient fire, and through grand spiral galaxies that began their slow dance when the universe itself was still young. Tonight, we won't rush, and we won't overwhelm. Instead, we'll gently uncover truths both wondrous and serene about the universe's hidden architecture, its invisible forces, and the delicate threads of physics, time, and chemistry that connect everything you've ever known into a single, unfolding cosmic story. Some of what you hear may surprise you. Other discoveries might settle softly into your mind, like moonlight spilling onto still water. And if these peaceful explorations help you unwind or spark even the quietest flicker of curiosity, consider liking this video or subscribing. It helps other quiet souls find their way here, one sleepy mind at a time. But for now, take a slow, deep breath, let go of the day, and let's begin our gentle voyage through the cosmos. There are more stars in the observable universe than there are grains of sand on every beach, every desert, and every dune on our entire planet, combined, multiplied, and then multiplied again. When you look up at the night sky, the countless points of light seem almost infinite, twinkling, distant, eternal. But the reality is far more astonishing. Current astronomical estimates, refined by data from the Hubble Space Telescope and the James Webb Space Telescope, suggest that the observable universe contains roughly 2 trillion galaxies. And within each of those galaxies, there may be anywhere from a few million to several hundred billion stars. When you multiply those numbers together, you arrive at a total stellar population that exceeds 1022 to 1024 individual stars, a figure so immense it defies ordinary comprehension. Each of those stars is a seething sphere of plasma, held together by its own gravity and powered by nuclear fusion deep within its core. Some are small, cool red dwarfs that may burn for trillions of years, slowly fusing hydrogen into helium with quiet efficiency. Others are blazing blue supergiants, colossal, brilliant, and short-lived, burning through their nuclear fuel in just a few million years before ending their lives in spectacular supernova explosions. Our own Sun is a modest G-type main sequence star, neither the largest nor the smallest, but perfectly balanced to nurture life on a small, rocky world orbiting at just the right distance. It has already shone for 4.6 billion years and will continue to do so for another 5 billion before it swells into a red giant and gently fades away. These stars shine across distances so vast that their light takes millions or even billions of years to reach us. When you look at the Andromeda galaxy, visible to the naked eye as a faint smudge in the autumn sky, you're seeing light that began its journey 2.5 million years ago, when early humans were just beginning to walk the Earth. And if you gaze toward the faint glow of the quasar 3C273, you're seeing light that left its source over 2 billion years ago, when complex life was just beginning to flourish in Earth's oceans. This staggering abundance of stars is not random noise. It speaks to the profound scale, elegance, and intricate complexity of the cosmos, where every single star may cradle its own family of planets, its own narrative of formation, evolution, and perhaps even the quiet stirrings of life. It's a humbling thought that in this boundless ocean of light and energy, we occupy just one tiny world orbiting just one average star. And yet, that very star and the atoms within your body are part of the same cosmic story that stretches from the edge of time to the farthest reaches of space. You are not separate from the universe. You are woven into it, molecule by molecule, photon by photon. And speaking of scale, the observable universe stretches an astonishing 93 billion light-years from one end to the other. But this figure represents only the portion of the cosmos from which light has had time to reach us since the beginning of time itself. The Big Bang occurred approximately 13.8 billion years ago, and because light travels at a finite speed, about 300,000 kilometers per second, we might assume the observable universe could only be 13.8 billion light-years in radius. But space itself has been expanding during those 13.8 billion years, stretching the distance between us and the most distant objects whose light is only now arriving. As a result, the current proper distance to the edge of the observable universe is about 46.5 billion light-years in every direction, giving a total diameter of 93 billion light-years. This spherical region, our cosmic horizon, contains every galaxy, every quasar, every whisper of matter whose photons have journeyed across eons to arrive at our telescopes, satellites, and detectors. Yet this observable universe is almost certainly just a tiny fraction of what truly exists. Beyond this visible boundary, space likely continues, perhaps endlessly, perhaps infinitely, filled with galaxies we will never see, stars that will never shine in our sky, and mysteries forever hidden in darkness and silence. Their light simply hasn't reached us yet, and due to the accelerating expansion of space, driven by dark energy, much of it never will. Regions beyond a certain distance are receding from us faster than the speed of light, not because they're moving through space that quickly, but because the space between us is stretching so rapidly that light can never bridge the growing gap. This horizon isn't a wall or a physical edge. It's a threshold defined by time, light, and the finite age of the universe. It stands as a gentle reminder of the limits of human perception, and of the vast, silent unknown that still waits just beyond our view. Even as time passes and the horizon expands slightly, revealing a few more distant galaxies, the accelerating expansion ensures that much of the cosmos will remain forever out of reach. We are, in a very real sense, island observers in an ocean of unseeable reality. Now consider this: space itself is expanding. It's not that galaxies are merely flying apart through a static void, like shrapnel from an explosion. Instead, the very fabric of spacetime is stretching, carrying galaxies farther apart with every passing moment. Picture dots drawn on the surface of an inflating balloon. As the balloon expands, the dots move away from each other, not because they're moving on their own, but because the surface between them is growing. In the same way, the universe's expansion increases the distances between galaxy clusters over time, not through motion in space, but through the growth of space itself. This expansion affects everything, from how light travels across the void to the ultimate fate of the cosmos. It's a slow but relentless transformation, quietly reshaping the grand architecture of space and time. And it's not uniform on small scales. Gravity binds galaxies, solar systems, and even you and Earth together so tightly that expansion has no effect locally. But on the largest scales, between galaxy clusters, the stretching of space dominates. This is why distant galaxies appear to be moving away from us, and the farther away they are, the faster they recede, a relationship known as Hubble's law. The Big Bang wasn't actually an explosion in space. It was the birth of space and time themselves, often imagined as a gigantic detonation within a pre-existing emptiness. The Big Bang was far more profound. There was no before the Big Bang because time did not exist. There was no outside because space had not yet come into being. In the beginning, all of existence, energy, matter, space, and time, was compressed into a state of unimaginable density and temperature. Then, in a moment that redefines our understanding of reality, space began to expand, time began to flow, and the fundamental laws of physics took hold. This initial expansion wasn't a blast within an existing void. It was the rapid unfolding of all of space itself. It's a concept that challenges our everyday intuition and reminds us just how mysterious and unique the origins of the universe truly are. There was no center, no edge, no direction, just an everywhere that began to grow. And from that fiery dawn, a whisper remains. Ancient light from the universe's earliest moments still fills every corner of space. This is the cosmic microwave background, CMB, a faint, nearly uniform glow of microwave radiation that permeates the entire cosmos. It dates back nearly 13.8 billion years, to a time just 380,000 years after the Big Bang, when the universe had cooled enough, from a searing 3,000 Kelvin down to about 3,000 K, for protons and electrons to combine into neutral hydrogen atoms. Before this moment of recombination, the universe was a hot, dense plasma of charged particles and photons. Light couldn't travel freely. It was constantly scattered, absorbed, and re-emitted in an endless dance of interaction. The cosmos was opaque, like the inside of the sun. But once neutral atoms formed, photons were suddenly freed, released in a great final scattering event known as last scattering. That light has been traveling ever since, stretched by the expansion of space from visible wavelengths into the microwave part of the spectrum. Today, the CMB glows at just 2.725 Kelvin, a mere 2.7 degrees above absolute zero. It is the oldest light we can observe, a true baby picture of the universe. Detected in every direction with exquisite precision by satellites like COBE, WMAP, and Planck, the CMB appears astonishingly uniform. Its temperature varies by only about 1 part in 100,000 across the entire sky. Yet within that near-perfect smoothness lie the seeds of all cosmic structure. These tiny temperature fluctuations, some regions slightly warmer, others slightly cooler, correspond to slight differences in density in the early universe. Over billions of years, gravity amplified these variations. Denser regions pulled in more matter, eventually collapsing to form galaxies, clusters, and the vast cosmic web we see today. The Planck satellite, which mapped the CMB from 2009 to 2013, measured these fluctuations with unprecedented detail. It revealed the universe's composition: 68.3% dark energy, 26.8% dark matter, and only 4.9% ordinary matter, the stuff of stars, planets, and us. It confirmed the universe is geometrically flat to within 0.2%, a key prediction of cosmic inflation. And it gave us the most precise age of the universe, 13.787 billion years, give or take 20 million. But the CMB holds even deeper secrets in its polarization. Just as sunlight reflecting off water becomes polarized, the scattering of photons at last scattering imprinted a subtle orientation on the CMB's light waves. This polarization comes in two patterns: E modes, caused by density fluctuations already detected, and B modes, which could be generated by primordial gravitational waves from cosmic inflation. Finding B modes would be like hearing the first note of the universe's symphony, a direct probe of physics at energies 1 trillion times greater than the Large Hadron Collider. Though not yet confirmed, experiments like BICEP, Keck, and future missions like Lightbird are hunting for this elusive signal. The CMB also exhibits a dipole anisotropy, a slight warming in one direction and cooling in the opposite, caused by our motion relative to the rest frame of the early universe. Once this motion is subtracted, the underlying fluctuations reveal the true primordial seeds. These fluctuations follow a precise statistical pattern known as a power spectrum, with distinct peaks that correspond to sound waves rippling through the primordial plasma, baryon acoustic oscillations, frozen in time at recombination. This ancient radiation is more than leftover heat. It's a time capsule, a photograph of the infant universe, and it surrounds us right now, as a whisper from the dawn of time, cool and constant, filling every cubic centimeter of space. As you rest in this moment, remember, the same photons that touched the first atoms are passing through you now. You are bathed in the afterglow of creation itself, a silent, eternal embrace from the beginning of everything. Though it emits no light and reveals itself only through gravity, dark matter forms an invisible framework that holds galaxies together. This mysterious substance, undetectable by any form of electromagnetic radiation, makes up approximately 85% of all matter in the universe. It does not absorb, reflect, or emit light, rendering it completely invisible to every telescope ever built. Yet its gravitational influence is undeniable. Without dark matter, galaxies would lack the necessary mass to keep their stars from flying apart as they rotate at tremendous speeds. The visible stars, gas, and dust simply don't provide enough gravity. Instead, each galaxy is embedded within a vast, diffuse halo of dark matter that extends far beyond its luminous edge, acting like an unseen skeleton that gives cosmic structures their form and stability. We detect dark matter only indirectly through its gravitational effects. One of the most compelling methods is gravitational lensing. When light from a distant galaxy passes near a massive foreground object, like a galaxy cluster, the gravity of that object bends and distorts the light, much like a lens. The amount of distortion often far exceeds what the visible mass can account for, revealing the presence of unseen matter. By mapping these distortions across the sky, astronomers have constructed detailed 3D maps of dark matter's distribution, revealing that it doesn't just surround galaxies, but forms a vast, interconnected cosmic web that spans the observable universe. And acting upon this hidden architecture is an even more enigmatic force, dark energy. For most of the 20th century, scientists assumed the universe's expansion, born in the Big Bang, was gradually slowing down due to the mutual gravitational attraction of all matter. But in 1998, two independent teams studying distant supernovae made a stunning discovery. The expansion is accelerating, not slowing, not stabilizing, speeding up. This acceleration is driven by dark energy, a mysterious form of energy that permeates all of space and behaves like a kind of anti-gravity. It accounts for nearly 70% of the total energy content of the universe. Unlike matter, which clumps and pulls, dark energy appears perfectly uniform and exerts a repulsive effect that pushes space itself apart at an ever-increasing rate. The leading explanation is Einstein's cosmological constant, a fixed energy density inherent to the vacuum of space. But other theories suggest dark energy could be a dynamic field, dubbed quintessence, that changes over time. Whatever its nature, dark energy will likely determine the ultimate fate of the cosmos. A cold, empty expansion into infinite darkness, where galaxies beyond our local group disappear over the cosmic horizon, never to be seen again. Galaxies, far from being scattered at random, are intricately organized by this hidden framework. They form part of a vast cosmic web, an enormous network of filaments made mostly of dark matter, stretching across hundreds of millions of light years. Along these invisible threads, galaxies cluster like dewdrops on a spider's silk. Between them lie immense cosmic voids, nearly empty regions that can span tens to hundreds of millions of light years, containing only sparse gas, a few scattered galaxies, and dark matter. This sponge-like structure, dense nodes linked by filaments, surrounded by voids, is the large-scale blueprint of the universe, shaped over billions of years by gravity acting on the initial seeds laid down in the Big Bang. Our own home, the Milky Way, is caught in this grand motion. It spins at over 500,000 miles per hour, a majestic whirl of stars, gas, and dust held together by gravity and by the unseen embrace of its dark matter halo. Our solar system orbits the galactic center once every 250 million years, riding this cosmic carousel through spiral arms, interstellar clouds, and regions of ancient and newborn stars. Despite this dizzying speed, the vast distances between stars mean actual collisions are extraordinarily rare, like firing two needles across continents and expecting them to hit. Still, this motion reminds us that we are not static observers. We are travelers on a dynamic voyage through the galaxy. And galaxies themselves are not eternal islands. Over billions of years, they drift, interact, and sometimes collide in slow gravitational embraces. When two galaxies come close enough, their mutual gravity draws them into a slow, elegant dance that can last for hundreds of millions to billions of years. Stars rarely crash into one another. Their distances are too great, but the gravitational tides distort their shapes, compress gas clouds, and trigger bursts of new star formation. In many cases, the galaxies eventually merge, forming a single larger galaxy. Our own Milky Way is already tugging at smaller satellite galaxies like the Large Magellanic Cloud, and in about 4.5 billion years, it will begin merging with the Andromeda Galaxy, creating a new elliptical galaxy astronomers sometimes call Milkdromeda. This process of galactic cannibalism is a key driver of cosmic evolution, building the massive galaxies we see in the universe's densest regions. Among the brightest objects in the cosmos are quasars, luminous beacons from the edge of time. Short for quasi-stellar radio sources, quasars shine from the hearts of young, distant galaxies, powered by supermassive black holes actively devouring surrounding gas and dust. As matter spirals into these black holes at nearly the speed of light, it forms an accretion disk heated to billions of degrees by friction and magnetic forces. This process converts gravitational energy into light with staggering efficiency, outshining entire galaxies of stars by factors of 100 or 1,000. Some quasars emit more energy in a single second than our Sun will in its entire 10 billion year life. Because their light takes billions of years to reach us, quasars act as cosmic lighthouses, illuminating the conditions of the early universe. Their spectra reveal the composition of intergalactic gas, the growth of black holes, and the epoch of reionization. They also serve as background sources for studying gravitational lensing and the distribution of dark matter across cosmic time. This brings us back to the universe's first fraction of a second, specifically, a period called cosmic inflation. According to leading theories, the universe underwent a burst of exponential expansion just 10.3 to 10.32 seconds after the Big Bang. During this unimaginably brief moment, space itself expanded faster than the speed of light, allowed by general relativity, since it's space stretching, not matter moving through space. Inflation explains three profound puzzles: why the universe appears so uniform in all directions, solving the horizon problem, why its geometry is so flat, the flatness problem, and why we don't see exotic relics like magnetic monopoles. Crucially, inflation, also magnified quantum fluctuations, tiny ripples in energy density arising from the uncertainty principle, stretching them from subatomic scales to cosmic proportions. These amplified fluctuations became the seeds for all future structure. The slight overdensities that under gravity would grow into galaxies, clusters, and filaments over 13.8 billion years. The imprint of these seeds is visible today as tiny temperature variations in the cosmic microwave background, observed with exquisite precision by satellites like Planck. Before any of this structure existed, however, the universe was dark. For hundreds of millions of years after the Big Bang, there were no stars, no galaxies, just a cooling sea of neutral hydrogen and helium gas, opaque to ultraviolet light. Then gravity pulled matter into denser clumps, and the first stars ignited. These population III stars, massive, hot, and short-lived, ended the cosmic dark ages in a blaze of ultraviolet radiation. Their light began to reionize the surrounding hydrogen gas, stripping electrons from atoms and transforming the foggy, opaque early universe into a transparent expanse where photons could finally travel unimpeded. This era, known as the Cosmic Dawn and the subsequent epoch of reionization, marked the universe's transition from darkness to light. It was not a single event, but a gradual process that took several 100 million years, ending around 1 billion years after the Big Bang. The James Webb Space Telescope is now peering into this era, detecting some of the earliest galaxies whose collective light completed the reionization of the cosmos. Meanwhile, high-energy particles known as cosmic rays streak through space at nearly the speed of light. Mostly protons and atomic nuclei, they are accelerated by violent events like supernova shock waves, pulsar winds, and jets from active black holes. When they strike Earth's atmosphere, they create air showers, cascades of secondary particles like muons and electrons that can even reach the ground. Some scientists suggest these rays may subtly influence cloud formation by ionizing atmospheric molecules, though this remains debated. More concretely, cosmic rays serve as direct messengers from the universe's most energetic phenomena, linking our planet to distant stellar cataclysms. Our Milky Way is not alone in the void. It belongs to a massive structure called the Laniakea supercluster, a gravitational metropolis containing over 100,000 galaxies spread across 520 million light-years. Within Laniakea, galaxies flow like rivers toward a dense core known as the Great Attractor, guided by the combined gravity of dark matter and visible mass. This motion, called peculiar velocity, reveals the large-scale flow of matter through the cosmic web. Understanding our place within Laniakea helps astronomers map the universe's gravitational landscape and test models of cosmic evolution. Between these clusters and superclusters lie the voids, vast, nearly empty regions that dominate the volume of the universe. Though they contain very little matter, voids are not passive gaps. Their low density creates subtle gravitational effects that push surrounding galaxies outward, shaping the motion of the cosmic web. Recent studies suggest voids may expand faster than average due to dark energy, offering a unique laboratory to test its properties. Studying voids also helps scientists understand how galaxies evolve in isolation, without the influence of neighbors. And passing through all of this, through galaxies, voids, planets, and even your own body, are neutrinos. These nearly massless, chargeless particles are produced in enormous numbers by the Sun, supernovae, and the Big Bang itself. Trillions of them stream through you every second, interacting so weakly with matter that they pass through the entire Earth as if it weren't there. A sea of relic neutrinos, created just 1 second after the Big Bang, still fills the cosmos, older even than the cosmic microwave background. Though we haven't yet detected these primordial neutrinos directly, they're too low energy for current detectors. Their gravitational influence helped shape the formation of galaxies. They are silent witnesses to the universe's first moments, ghostly threads connecting us to the dawn of time. On the largest scales, the universe appears remarkably uniform, a principle known as cosmological homogeneity and isotropy. No matter where we look, the distribution of galaxies and matter is statistically the same. This smoothness, confirmed by the near-uniform temperature of the cosmic microwave background, varying by only 1 part in 100,000, underpins our entire understanding of cosmic evolution. It suggests that the laws of physics operate the same everywhere, allowing us to build universal models of the cosmos. Yet this uniformity hides a deeper mystery. Why does the universe consist almost entirely of matter, with almost no antimatter? The Big Bang should have created equal amounts of both, which would have annihilated each other, leaving behind only pure energy. The fact that we, and everything we see, exist means that some unknown process in the early universe favored matter over antimatter by about 1 part in 10 billion. This baryon asymmetry remains one of the greatest unsolved problems in physics, possibly involving violations of CP symmetry or processes in grand unified theories. Even light itself carries the imprint of this hidden architecture. As photons travel across billions of light years, their paths are gently bent by the gravity of galaxies and dark matter, a phenomenon called gravitational lensing. This distortion subtly warps the cosmic microwave background and magnifies distant galaxies, acting as a natural telescope. By studying these effects, astronomers can map the invisible distribution of mass, revealing the dark skeleton of the cosmos. And so, as space expands and galaxies drift, their light stretches into longer, redder wavelengths, a cosmic signature known as redshift. This effect, first observed by Edwin Hubble in the 1920s, provides direct evidence of the universe's expansion. By measuring redshift, astronomers can determine how fast galaxies are receding and how far away they are, effectively looking back in time. Combined with tools like Cepheid variable stars, whose pulsation period reveals their true brightness, and Type Ia supernovae, standard candles with consistent peak luminosity, redshift forms the backbone of the cosmic distance ladder, allowing us to chart the universe's vast expanse with increasing precision. But there's a growing puzzle in this ladder, the Hubble tension. Measurements of the universe's current expansion rate, the Hubble constant, from the early universe, using the CMB and lambdactum model, yield a value of about 67 km/s per megaparsec. But measurements from the late universe, using Cepheids and supernovae, give 73 km/s per megaparsec. This discrepancy, now confirmed at over 5 sigma, suggests either unknown systematic errors or new physics beyond our current model. Perhaps evolving dark energy, exotic neutrino properties, or modifications to gravity itself. Our view, however, is bounded by the cosmic horizon, the limit of how far light has traveled since the Big Bang. Because the universe is 13.8 billion years old, we cannot see beyond a sphere roughly 46.5 billion light-years in radius, the 93 billion light-year diameter. Beyond this lies space whose light hasn't reached us yet, and may never will, due to accelerating expansion. This horizon is not a wall, but a frontier of knowledge, reminding us that the observable universe is only a part of a much grander whole. Tiny grains of cosmic dust drift through the void, silently shaping the destiny of stars and planets. Though each speck is smaller than a micron, less than the width of a human hair, these particles are made of carbon, silicon, oxygen, and metals forged in the hearts of dying stars. Within vast molecular clouds, cold and dense with gas, these dust grains act as cosmic refrigerators. They radiate away heat through infrared emission, allowing the cloud to cool and collapse under its own gravity. Without this cooling, gas pressure would resist collapse, and stars might never ignite. Thus, dust is not mere debris, it is a catalyst for creation. Around newborn stars, dust takes on another role. In the swirling protoplanetary disks that orbit infant suns, microscopic grains gently collide and stick together, first through electrostatic forces, then through gravity, growing from specks to pebbles, boulders, and eventually planetesimals. Over millions of years, These coalesce into rocky planets, icy moons, and asteroid belts. But dust does more than build worlds. It provides surfaces where atoms can meet, bond, and form complex molecules. In the icy mantles of cold dust grains, simple compounds like water, methane, and ammonia combine into organic molecules, including amino acids, the building blocks of proteins. In this quiet alchemy, the chemistry of life begins, suspended in the inky dark between stars. The universe's very first stars were unlike any we see today. Born from pristine clouds containing only hydrogen and helium, the lightest elements forged in the Big Bang, these ancient giants, known as population III stars, burned hotter, brighter, and far more briefly than most modern stars. With no heavier elements to enrich their chemistry, they could not cool efficiently, so they formed only in massive clumps, tens or even hundreds of times the mass of our Sun. They lived fast, burning their nuclear fuel in just a few million years before exploding as supernovae, scattering the first carbon, oxygen, iron, and other heavy elements into the void. These explosions were the universe's first act of chemical enrichment. Though none of these primordial stars remain, their explosive legacies echo in every atom of our bodies. Hidden behind thick veils of this same cosmic dust, distant galaxies glow brightly, but not invisible light. Dust absorbs the intense ultraviolet and visible light from furious bursts of star formation and re-emits it as infrared radiation. Optical telescopes see only darkness, but infrared observatories, like the James Webb Space Telescope, peer through these dusty shrouds, revealing galaxies in their most active, formative stages. These hidden stellar nurseries help astronomers understand how galaxies assembled their mass, how stars ignited in the early universe, and how the cosmic web evolved over billions of years. Cosmic rays may also subtly influence Earth's weather and climate. When these high-energy particles strike the upper atmosphere, they ionize molecules, potentially providing nucleation sites for water droplets to form clouds. While the magnitude of this effect is still debated, it represents a fascinating link between distant supernovae and terrestrial meteorology, a reminder that Earth is not isolated, but immersed in the galaxy's energetic flow. Billions of years ago, the universe reached its peak of stellar creativity, a golden era astronomers call cosmic high noon. During this time, roughly 10 billion years ago, galaxies were forming stars at rates 10 to 30 times higher than today. The universe was rich with cold gas, turbulent with collisions, and ablaze with newborn suns. This surge filled space with heavier elements, enriching the interstellar medium and setting the stage for rocky planets and complex chemistry. Since then, star formation has gradually declined as galaxies used up or expelled their gas. Today, the Milky Way forms only 1-2 new stars per year, a quiet echo of its fiery youth. The elements that make up our world, oxygen in the air, calcium in our bones, iron in our blood, were all forged inside stars. The Big Bang produced only hydrogen, helium, and trace lithium. Everything else was created through nuclear fusion in stellar cores or during the cataclysmic explosions of massive stars. In red giants, carbon and oxygen are cooked. In supernovae, elements like silicon, sulfur, and iron are forged. In neutron star mergers, gold, platinum, and uranium are born. When those stars died, they scattered these elements into space, where they were recycled into new stars, planets, and eventually living beings. At the hearts of many galaxies, supermassive black holes unleash powerful jets of charged particles traveling near the speed of light. These jets can stretch for millions of light years, far beyond the visible edges of their host galaxies. By heating and pushing away surrounding gas, they regulate star formation, sometimes stifling it by blowing gas out of the galaxy, sometimes triggering bursts by compressing clouds. These black holes are not just destroyers, they are cosmic regulators, shaping the evolution of entire galaxies through their energetic feedback. Measurements from the Planck satellite and other observatories show that the universe is astonishingly flat, not curved like a sphere or a saddle. This flat geometry implies a precise balance between the universe's total energy density and its expansion rate. A flat universe means that parallel lines stay parallel even over cosmic distances, and it strongly supports the theory of cosmic inflation. This flatness also suggests the universe will continue expanding forever, growing ever colder and more diffuse, a fate dictated by the delicate equilibrium of its birth. Yet this timeline comes with a fundamental limitation. We can observe only one universe. This constraint, known as cosmic variance, means that any measurement, whether of galaxy clustering or fluctuations in the cosmic microwave background, is based on a single cosmic sample. Without multiple universes to compare, it's impossible to know whether certain patterns are universal laws or just random quirks of our cosmic neighborhood. This uncertainty humbles our knowledge and reminds us that we view the cosmos from a single, unique vantage point. Some theories suggest that cosmic strings, hypothetical thread-like defects in spacetime, may have formed in the universe's first fraction of a second during phase transitions as fundamental forces separated. If they exist, these ultra-dense filaments could stretch across the cosmos, warping spacetime and potentially generating gravitational waves. Though no evidence has yet been found, cosmic strings remain a fascinating possibility that could reveal secrets about the unification of fundamental forces. High-energy X-rays glow from the hearts of distant galaxies, emitted by supermassive black holes devouring matter. As gas spirals inward, it heats to millions of degrees, releasing X-rays detectable by space telescopes like Chandra. These X-ray sources reveal the most violent processes in the universe: black holes growing, jets launching, gas being shredded. Pulsars, rapidly spinning neutron stars, send beams of radio waves sweeping through space like cosmic lighthouses. Alongside T. Distant galaxies emit diffuse radio waves from star formation and black hole jets. Radio astronomy reveals a hidden universe, magnetic fields, cold gas, and exotic objects invisible in optical light. Gamma ray bursts, brief, powerful flashes of high-energy light, are among the universe's most energetic events. Lasting from milliseconds to minutes, they signal the death of massive stars or the merger of neutron stars. In seconds, they can outshine entire galaxies. The CMB also carries polarization patterns, subtle alignments in the orientation of its light waves. These patterns encode information about gravitational waves from the universe's first fraction of a second and the density ripples that seeded galaxies. Scientists are still searching for the faintest of these signals, called B-modes, which could provide direct evidence of cosmic inflation. As you rest now, consider this. The same physical laws that govern a falling apple also shape the motion of galaxy clusters billions of light-years away. The same hydrogen atoms formed in the first minutes after the Big Bang fueled the stars that light the night sky. You are not separate from this grand unfolding. You are a conscious expression of it, breathing stardust, dreaming beneath ancient light. Tiny grains of cosmic dust drift through the void, silently shaping the destiny of stars, planets, and perhaps even life itself. Though each speck is smaller than a micron, less than the width of a human hair, these particles are rich in carbon, silicon, oxygen, and metals forged in the hearts of dying stars. Within vast molecular clouds, cold and dense with gas, these dust grains act as cosmic refrigerators. They radiate away heat through infrared emission, allowing the cloud to cool and collapse under its own gravity. Without this cooling, gas pressure would resist collapse, and stars might never ignite. Thus, dust is not mere debris, it is a catalyst for creation, a quiet midwife to new suns. Around newborn stars, dust takes on another role. In the swirling protoplanetary disks that orbit infant suns, microscopic grains gently collide and stick together, first through electrostatic forces, then through gravity, growing from specks to pebbles, boulders, and eventually planetesimals. Over millions of years, these coalesce into rocky planets, icy moons, and asteroid belts. But dust does more than build worlds. It provides surfaces where atoms can meet, bond, and form complex molecules. In the icy mantles of cold dust grains, simple compounds like water, methane, and ammonia combine into organic molecules, including amino acids, the building blocks of proteins. In this quiet alchemy, suspended in the inky dark between stars, the chemistry of life begins. The universe's very first stars were unlike any we see today. Born from pristine clouds containing only hydrogen and helium, the lightest elements forged in the Big Bang, these ancient giants, known as population III stars, burned hotter, brighter, and far more briefly than most modern stars. With no heavier elements to enrich their chemistry, they could not cool efficiently, so they formed only in massive clumps, tens or even hundreds of times the mass of our Sun. They lived fast, burning their nuclear fuel in just a few million years before exploding as supernovae, scattering the first carbon, oxygen, iron, and other heavy elements into the void. These explosions were the universe's first act of chemical enrichment. Though none of these primordial stars remain, their explosive legacies echo in every atom of our bodies. You are quite literally made of the ashes of the first stars. Hidden behind thick veils of this same cosmic dust, distant galaxies glow brightly, but not in visible light. Dust absorbs the intense ultraviolet and visible light from furious bursts of star formation and re-emits it as infrared radiation. Optical telescopes see only darkness, but infrared observatories like the James Webb Space Telescope peer through these dusty shrouds, revealing galaxies in their most active, formative stages. These hidden stellar nurseries help astronomers understand how galaxies assembled their mass, how stars ignited in the early universe, and how the cosmic web evolved over billions of years. Without infrared vision, we would be blind to half the story of cosmic evolution. This transformation from darkness to light was not instantaneous. After the Big Bang, the universe spent hundreds of millions of years in a cold, opaque silence, a period known as the Cosmic Dark Ages. It ended only when the first stars and galaxies began to shine. Their fierce ultraviolet radiation ionized the surrounding hydrogen gas, stripping electrons from atoms and turning the foggy, neutral medium into a transparent plasma. This epoch, called reionization, cleared the cosmic haze, allowing light to travel freely for the first time. It was a fundamental turning point, the moment the universe became transparent, vibrant, and observable, without ray. Ionization, the cosmos would remain a dark, featureless fog. No stars visible, no galaxies mapped, no light to guide us. Billions of years ago, the universe reached its peak of stellar creativity, a golden era astronomers call cosmic high noon. During this time, roughly 10 billion years ago, galaxies were forming stars at rates 10 to 30 times higher than today. The universe was rich with cold gas, turbulent with collisions, and ablaze with newborn suns. This surge filled space with heavier elements, enriching the interstellar medium and setting the stage for rocky planets and complex chemistry. Since then, star formation has gradually declined as galaxies used up or expelled their gas. Today, the Milky Way forms only 1-2 new stars per year, a quiet echo of its fiery youth. We live in a mature cosmos where creation continues, but at a gentler pace. The elements that make up our world, oxygen in the air, calcium in our bones, iron in our blood, were all forged inside stars. The Big Bang produced only hydrogen, helium, and trace lithium. Everything else was created through nuclear fusion in stellar cores or during the cataclysmic explosions of massive stars. In red giants, carbon and oxygen are cooked. In supernovae, elements like silicon, sulfur, and iron are forged. In neutron star mergers, gold, platinum, and uranium are born. When those stars died, they scattered these elements into space, where they were recycled into new stars, planets, and eventually living beings. You are quite literally made of stardust, an intimate heir to the life and death of ancient suns. At the hearts of many galaxies, supermassive black holes unleash powerful jets of charged particles traveling near the speed of light. These jets can stretch for millions of light years, far beyond the visible edges of their host galaxies. By heating and pushing away surrounding gas, they regulate star formation, sometimes stifling it by blowing gas out of the galaxy, sometimes triggering bursts by compressing clouds. These black holes are not just destroyers, they are cosmic regulators, shaping the evolution of entire galaxies through their energetic feedback. Observing these jets reveals the dynamic partnership between black holes and the galaxies they inhabit, a dance of destruction and creation that has sculpted the cosmos for billions of years. High-energy cosmic rays, born in supernova explosions and black hole jets, travel across the galaxy and occasionally reach Earth. When they strike our atmosphere, they create cascades of secondary particles that can penetrate to the surface and even into living cells. There, they sometimes cause mutations in DNA. While most of these changes are repaired or harmless, a few may contribute to genetic variation over evolutionary time. In this subtle way, violent cosmic events far beyond our solar system have quietly influenced the course of life on Earth, linking our biological story to the wider universe. You carry within you not just stardust, but cosmic scars, tiny imprints of distant explosions woven into your genetic code. Invisible magnetic fields thread through galaxies like unseen currents, guiding the motion of charged particles and influencing how gas collapses to form stars. Though weaker than Earth's magnetic field, typically a few microgauss, these galactic fields span tens of thousands of light years, shaping the structure of spiral arms and the flow of interstellar material. They also help confine cosmic rays, channeling them along magnetic highways that crisscross the Milky Way. These invisible forces add a hidden layer of complexity to the cosmic tapestry, reminding us that the universe operates through more than just gravity and light. These same cosmic rays, along with particles from the Sun, help create one of Earth's most beautiful phenomena, the auroras, or northern and southern lights. When high-energy particles collide with gases in our upper atmosphere near the poles, they excite oxygen and nitrogen atoms, causing them to glow in vibrant hues of green, red, and purple. This dazzling display is a direct connection between distant cosmic violence and earthly wonder, a reminder that our planet is bathed in the gentle rain of the cosmos. Some theories suggest that cosmic strings, hypothetical thread-like defects in spacetime, may have formed in the universe's first fraction of a second during phase transitions as fundamental forces separated. If they exist, these ultra-dense filaments could stretch across the cosmos, warping spacetime and potentially generating gravitational waves. Though no evidence has yet been found, cosmic strings remain a fascinating possibility that could reveal secrets about the unification of fundamental forces and the quantum nature of the early universe. They represent a bridge between the infinitesimal and the infinite. Measurements from the Planck satellite and other observatories show that the universe is astonishingly flat, not curved like a sphere or a saddle. This flat geometry implies a precise balance between the universe's total energy density and its expansion rate. A flat universe means that parallel lines stay parallel even over cosmic distances, and it strongly supports the theory of cosmic inflation, which predicts such smoothness. This flatness also suggests the universe will continue expanding forever, growing ever colder and more diffuse, a fate dictated by the delicate equilibrium of its birth. Astronomers estimate the ages of distant galaxies by analyzing the light they emit. Because light takes time to travel, observing a galaxy billions of light years away is like looking back in time. By studying the colors and spectra of its stars, particularly the presence of red giants, main sequence turnoffs, and metal lines, scientists can determine when those stars formed and how the galaxy evolved. This cosmic archaeology helps build a timeline of the universe, from the fiery aftermath of the Big Bang to the structured, star-filled cosmos we see today. Each galaxy is a time capsule, preserving a chapter in the grand narrative of cosmic evolution. Yet this timeline comes with a fundamental limitation. We can observe only one universe. This constraint, known as cosmic variance, means that any measurement, whether of galaxy clustering or fluctuations in the cosmic microwave background, is based on a single cosmic sample. Without multiple universes to compare, it's impossible to know whether certain patterns are universal laws or just random quirks of our cosmic neighborhood. This uncertainty humbles our knowledge and reminds us that we view the cosmos from a single, unique vantage point. Galaxies themselves grow through slow mergers, colliding and combining over billions of years. These encounters rarely involve star-to-star crashes. Space is too vast for that, but they dramatically reshape galaxies, triggering bursts of star formation and feeding central black holes. Our Milky Way is already pulling in smaller satellite galaxies like the Sagittarius dwarf spheroidal, and is destined to merge with Andromeda in about 4.5 billion years. Through this gradual cosmic accretion, galaxies evolve from small, irregular clumps into grand spirals or smooth ellipticals. You are living in a galaxy that is still growing, still eating its neighbors, still changing. Even in the emptiest regions, cosmic voids influence the motion of galaxies around them. Their low density creates subtle gravitational pushes that help shape the flow of matter along the cosmic web. Studying these voids offers clues about dark energy, since voids may expand faster in a dark energy-dominated universe, and the distribution of dark matter. Voids are not passive gaps. They are dynamic participants in cosmic evolution, their emptiness helping define the structure of everything around them. High-energy X-rays glow from the hearts of distant galaxies, emitted by supermassive black holes devouring matter. As gas spirals inward, it heats to millions of degrees, releasing X-rays detectable by space telescopes like Chandra. These X-ray sources reveal the most violent processes in the universe: black holes growing, jets launching, gas being shredded. They also trace the hot intergalactic medium in galaxy clusters, mapping the invisible scaffolding of the cosmos. Turbulent gas clouds within galaxies shape star formation in profound ways. Stirred by supernova explosions, spiral density waves, and magnetic fields, this turbulence compresses pockets of gas, triggering gravitational collapse. The balance between turbulence and gravity determines how many stars form, how massive they become, and how clustered they appear. This chaotic yet ordered process governs the life cycle of galaxies, turning gas into stars in an endless cycle of birth and death. Pulsars, rapidly spinning neutron stars, send beams of radio waves sweeping through space like cosmic lighthouses. Alongside them, distant galaxies emit diffuse radio waves from star formation and black hole jets. Radio astronomy reveals a hidden universe: magnetic fields, cold gas, and exotic objects invisible in optical light. By listening to this radio symphony, scientists map the unseen architecture of the cosmos. Gamma-ray bursts, brief, powerful flashes of high-energy light, are among the universe's most energetic events. Lasting from milliseconds to minutes, they signal the death of massive stars or the merger of neutron stars. In seconds, they can outshine entire galaxies. These bursts serve as probes of the early universe, revealing conditions when the first stars died and black holes formed. Bubble-like structures may have formed during early cosmic phase transitions, as symmetries broke and forces separated. If these bubbles collided, they might have generated gravitational waves, a potential signal for future observatories like LISA. Such relics would offer a direct window into physics at energies far beyond the reach of particle colliders. And through it all, light itself carries the story. As it travels across expanding space, its waves stretch into longer, redder wavelengths, a cosmic signature called redshift. This effect allows astronomers to measure distances, look back in time, and reconstruct the history of cosmic expansion. Every photon is a messenger from the past, carrying news from galaxies as they were billions of years ago. The cosmic microwave background also carries polarization patterns, subtle alignments in the orientation of its light waves. These patterns encode information about gravitational waves from the universe's first fraction of a second and the density ripples that seeded galaxies. Scientists are still searching for the faintest of these signals, called B-modes, which could provide direct evidence of cosmic inflation. Reionization was more than a change in gas. It was a transformation of the universe's very nature. By making space transparent to ultraviolet light, it allowed photons to travel unimpeded for the first time since the Big Bang. This not only illuminated the cosmos, but also changed how structures could form. Gas could cool more efficiently, stars could shine farther, and galaxies could grow in complexity. Reionization wasn't just an event, it was a threshold. The moment the universe stepped out of its dark, formative childhood and into maturity. Cosmic dawn, then, was not just the first light, but the first lasting light. The first sustained illumination that would never fade. It marked the point when the universe became capable of memory, of structure, of story. From that dawn emerged the galaxies that would collide, merge, and evolve into the cosmic tapestry we map today. Understanding this era is like reading the first sentence of a book that contains everything. As you rest now, remember, you are not separate from this vast unfolding. The iron in your blood was forged in a supernova. The oxygen you breathe was cooked in a red giant. The calcium in your bones was scattered by a dying star. You are a living echo of the universe's oldest fires, a conscious fragment of cosmic dust, dreaming beneath a sky filled with ancient light. The universe's oldest light carries a temperature just a few degrees above absolute zero, a faint, pervasive chill that fills all of space like a silent breath from the dawn of time. This is the cosmic microwave background, CMB, the cooled remnant of the Big Bang's searing fire. Stretched and cooled over 13.8 billion years by the relentless expansion of space, it now glows at a mere 2.725 Kelvin, just 2.7 degrees above absolute zero. Yet within this near-uniform coldness lie the subtlest of ripples, temperature variations of only a few parts in 100,000. These are not imperfections, they are blueprints. Each tiny fluctuation marks a region of slightly higher or lower density in the infant universe, and over billions of years, gravity amplified these whispers into the grand architecture of galaxies, clusters, and cosmic filaments we see today. This light was released at a precise moment, 380,000 years after the Big Bang, during an event called recombination. Before this, the universe was a hot, opaque plasma, so dense that photons couldn't travel more than a few centimeters before colliding with free electrons. Light was trapped in an endless fog. But as the cosmos expanded and cooled below 3000 Kelvin, electrons and protons combined to form neutral hydrogen atoms. Suddenly, photons were freed, released in a final universal scattering event known as last scattering. That light has been traveling ever since, stretched by cosmic expansion from visible wavelengths into microwaves. Today, it arrives from every direction, wrapping the Earth in a soft, ancient embrace. You are literally bathed in the afterglow of creation. Satellites like COBE, WMAP, and especially Planck have mapped this glow with exquisite precision. Planck's data confirmed that the universe is geometrically flat to within 0.2%, consistent with predictions from cosmic inflation. It measured the universe's composition with stunning clarity: 68.3% dark energy, 26.8% dark matter, and only 4.9% ordinary matter, the atoms that make up stars, planets, and us. It gave us the most accurate age of the cosmos, 13.787 billion years, with an uncertainty of just 20 million years. and it revealed the acoustic peaks in the CMB power spectrum, echoes of sound waves that rippled through the primordial plasma, frozen in time at recombination. These peaks are the universe's heartbeat, recorded in light. But the CMB holds even deeper secrets in its polarization. Just as sunlight reflecting off water becomes polarized, the scattering of photons at last scattering imprinted a subtle orientation on the CMB's light waves. This polarization comes in two patterns: E modes, caused by density fluctuations already detected, and B modes, which could be generated by primordial gravitational waves from cosmic inflation. Finding B modes would be like hearing the first note of the universe's symphony, a direct probe of physics at energies 1 trillion times greater than the Large Hadron Collider. Though not yet confirmed, experiments like BICEP, Keck, and future missions like Lightbird are hunting for this elusive signal. If found, it would confirm that inflation happened and reveal how violently space itself was born. High above Earth, cosmic ray showers cascade through the atmosphere in constant, invisible torrents. When energetic particles, mostly protons accelerated by supernova remnants or black hole jets, strike air molecules, they shatter into cascades of secondary particles, electrons, muons, pions, and photons. These showers spread like ripples in a pond, sometimes reaching the ground and even penetrating deep underground. Detectors like the Pier Auger Observatory track these events to trace cosmic rays back to their sources. Though invisible, these particles link our planet to the galaxy's most violent phenomena. They also interact with atmospheric chemistry, ionizing molecules and possibly influencing cloud formation, a subtle bridge between stellar death and Earth's climate. Though seemingly empty, cosmic voids are active participants in cosmic evolution. These vast regions, tens to hundreds of millions of light-years across, contain very little matter, but their low density creates a kind of gravitational repulsion. Surrounding galaxies flow away from voids and toward denser filaments and clusters, shaping the large-scale motion of the cosmic web. Recent studies suggest voids may expand faster than average due to dark energy, making them natural laboratories for testing its properties. By studying how galaxies move near voids, astronomers can map the invisible distribution of dark matter and probe the nature of gravity itself. From the hearts of galaxies, jets from supermassive black holes stretch for millions of light-years, carving paths through intergalactic space. Powered by the extreme gravity and twisted magnetic fields near the event horizon, these jets blast out charged particles at nearly the speed of light. In doing so, they heat surrounding gas, suppress star formation, or sometimes compress clouds and trigger new stellar birth. They are not just byproducts, they are feedback mechanisms regulating how galaxies grow. Without them, massive galaxies might form stars uncontrollably and burn out quickly. With them, galaxies evolve in balance. Observing these jets reveals how black holes and galaxies co-evolve, a partnership written in light and plasma across cosmic time. This transformation began during cosmic dawn, the era when the first galaxies lit up the universe after hundreds of millions of years of darkness. Before this, space was filled with neutral hydrogen gas, opaque to ultraviolet light. But as the first stars grouped into galaxies, their collective radiation began reionizing the surrounding gas, stripping electrons from atoms and turning the fog into transparent plasma. This epoch, lasting from about 400 million to 1 billion years after the Big Bang, marked the end of the cosmic dark ages. The James Webb Space Telescope is now peering into this era, detecting galaxies so distant their light has traveled over 13.4 billion years to reach us. These infant galaxies, small but fiercely luminous, were the universe's first architects, clearing the fog so future generations could see. Today, that ancient glow, the oldest light in existence, still fills space almost perfectly uniformly. Its smoothness is one of cosmology's great wonders, hinting at a universe that underwent rapid smoothing in its first instant. And yet, within that smoothness lie the seeds of galaxies, clusters, and filaments. This duality, uniformity and structure, stillness and motion, is the essence of the cosmos. The background light doesn't shout, it hums. And in that hum, the story of everything is written. By measuring the ages of distant galaxies, astronomers trace the timeline of cosmic history. Because light takes time to reach us, looking far away is the same as looking back in time. A galaxy 10 billion light-years away shows us what the universe looked like 10 billion years ago. By analyzing the colors and spectra of its stars, particularly the ratio of red giants to main sequence stars, scientists estimate when those stars formed, how quickly the galaxy grew, and how its chemistry evolved. This cosmic archaeology reveals a universe that was once wild with star formation, gradually settling into the calmer state we see today. Each galaxy is a time capsule, preserving a chapter in the grand narrative of cosmic evolution. This grand narrative is what we call cosmic evolution, the ongoing transformation of matter and energy from the hot, dense beginning to the rich, structured cosmos of today. It includes the birth of stars, the assembly of galaxies, the forging of elements, and the emergence of planets capable of hosting life. Nothing in the universe is static. Everything changes, flows, and evolves over billions of years. And we, made of atoms born in stars, are part of that evolution, not just witnesses to it. Yet our view is limited by a fundamental truth. We observe only one universe. This constraint, known as cosmic variance, means that every measurement of galaxy clustering, of microwave background ripples, is based on a single cosmic sample. There's no second universe to compare against, no control group. What we see might be typical, or it might be a rare cosmic accident. This uncertainty humbles our knowledge and reminds us that science, even at its most precise, is shaped by the uniqueness of our vantage point. Adding to this connection is the constant interplay between cosmic rays and the solar wind. The sun's magnetic field and outflowing plasma deflect many incoming cosmic rays, modulating how many reach Earth. During periods of high solar activity, fewer cosmic rays penetrate the inner solar system. During solar minimum, more arrive. This dance affects space weather, satellite operations, and even radiation exposure for astronauts. It's a subtle but real link between our star and the galaxy beyond, proof that even our local environment is shaped by forces light years away. Stretching across entire galaxies are magnetic fields, invisible but influential. Though far weaker than Earth's magnetism, typically a few microgauss, these fields span tens of thousands of light years, threading through spiral arms and halos. They guide the motion of cosmic rays, shape interstellar gas clouds, and help regulate how stars form. Without them, galaxies might evolve very differently. These magnetic threads are another hidden layer of cosmic structure, a silent force weaving through the visible universe. The process of reionization was more than a change in gas. It was a transformation of the universe's very nature. By making space transparent to ultraviolet light, it allowed photons to travel unimpeded for the first time since the Big Bang. This not only illuminated the cosmos, but also changed how structures could form. Gas could cool more efficiently, stars could shine farther, and galaxies could grow in complexity. Reionization wasn't just an event, it was a threshold. The moment the universe stepped out of its dark, formative childhood and into maturity. Cosmic dawn, then, was not just the first light, but the first lasting light, the first sustained illumination that would never fade. It marked the point when the universe became capable of memory, of structure, of story. From that dawn emerged the galaxies that would collide, merge, and evolve into the cosmic tapestry we map today. Understanding this era is like reading the first sentence of a book that contains everything. Some theories suggest that cosmic strings, hypothetical, ultra-dense filaments left over from the universe's first instance, might still stretch through space. If they exist, they would warp spacetime and possibly generate gravitational waves detectable by future observatories like LISA. Though none have been detected, their potential discovery would offer a direct window into physics at energies far beyond what particle colliders can reach. They represent the deep link between the quantum world and the cosmos, a thread connecting the smallest scales to the largest. And it was inflation that made the universe appear so smooth on grand scales. In a fraction of a second after the Big Bang, space expanded faster than light itself, smoothing out irregularities and stretching quantum fluctuations to cosmic size. Those fluctuations became the seeds we see in the microwave background, tiny ripples that over eons grew into galaxies. Inflation explains why opposite sides of the sky have the same temperature, even though they've never been in causal contact. It's a cornerstone of modern cosmology, elegantly bridging the unimaginably small and the unimaginably large. The photons from the Big Bang are more than relics, they are messengers. Each carries information about the density, temperature, and composition of the infant universe. By studying them, we learn how much dark matter exists, how fast the universe is expanding, and whether new physics might be at play. These ancient particles have traveled uninterrupted for nearly 14 billion years, arriving at our detectors with stories from the dawn of time. Over a century ago, scientists first discovered cosmic rays when instruments detected mysterious radiation increasing with altitude. Victor Hess's balloon flights in 1912 proved this radiation came from space, launching a new field of physics. Today, we know these rays are mostly protons and atomic nuclei, accelerated by supernova remnants and active black holes. They remind us that Earth is bathed in a constant rain of particles from across the galaxy, a subtle but continuous connection to the universe's most energetic events. Our view, however, is bounded by the cosmic horizon, the limit of how far light has traveled since the Big Bang. Because the universe is 13.8 billion years old, we cannot see beyond a sphere roughly 46.5 billion light-years in radius, the 93 billion light-year diameter. Beyond this lies space whose light hasn't reached us yet, and may never will due to accelerating expansion. This horizon is not a wall, but a frontier of knowledge, reminding us that the observable universe is only a part of a much grander whole. The cosmic microwave background captures a true snapshot of the young universe, frozen in time at 380,000 years old. Before this, the cosmos was a hot, opaque fog. After, it became transparent. That moment of last scattering imprinted the universe's density map onto the sky. Every telescope that observes the CMB is, in effect, looking at a baby picture of everything that would become stars, planets, and us. And in that light lies polarization, a subtle alignment of light waves that encodes even deeper secrets. Patterns in this polarization may reveal gravitational waves from inflation, offering direct evidence of the universe's exponential birth. Though incredibly faint, these signals could confirm theories about quantum gravity and the nature of spacetime itself. They are the universe's finest handwriting, barely legible, but profoundly meaningful. Much of the universe's ordinary matter, baryonic matter, the stuff of stars, planets, and people, resides not in galaxies, but in the cosmic filaments between them. This gas is hot and diffuse, glowing faintly in X-rays, and was long considered missing. Now we know it flows along the dark matter scaffolding, feeding galaxies and fueling star formation. The web isn't just structure, it's circulation, a cosmic bloodstream carrying the ingredients of life. Black hole jets, stretching millions of light years, are among the universe's most powerful engines. They can outshine entire galaxies and influence regions far beyond their host. By pushing gas away or compressing it, they act as both brakes and accelerators on galactic evolution. They are proof that even objects defined by what they consume can shape the cosmos by what they release. The imprints of inflation remain in the CMB, not as loud echoes, but as delicate patterns in temperature and polarization. These are the stretched quantum ripples, the original seeds. Finding them is like hearing the first note of a symphony that played for billions of years. They confirm that the universe's largest structures grew from the tiniest fluctuations, linking quantum uncertainty to galactic grandeur. Some researchers suggest cosmic rays may influence Earth's cloud formation. By ionizing molecules in the upper atmosphere, they could provide nucleation sites for water droplets. If true, this would mean distant supernovae subtly affect our weather, a poetic idea, though still debated. Either way, it underscores a deeper truth. Earth is not isolated. It is immersed in the galaxy's energetic flow. Galactic movements follow the cosmic web's contours. Galaxies flow along filaments like leaves on a river, pulled by gravity toward massive clusters. This motion, called peculiar velocity, reveals the distribution of dark matter and helps map the universe's hidden mass. The cosmos is not static. It is in constant, slow motion, guided by invisible currents. Finally, neutrinos, those ghostly particles born in the Big Bang's first second, still stream through space, forming a cosmic neutrino background. Though nearly impossible to detect, they shaped how matter clumped in the early universe. One day, if we can observe them directly, they will offer a view of the cosmos even earlier than the microwave background, back to 1 second after creation. And now, the vastness of the cosmos gently settles behind your thoughts. You have drifted through 100 quiet wonders, from the birth of the first stars to the silent pull of dark matter, from the faint echo of the Big Bang to the invisible rain of neutrinos. You have journeyed through star-filled nurseries, soared along luminous spiral arms, and glimpsed the heart of galaxies glowing across unimaginable distances. You are not separate from this story. You are woven into it. The calcium in your bones, the iron in your blood, the oxygen in your breath, all were forged in the cores of ancient stars that lived and died before the sun was born. You are stardust made conscious, a quiet presence in an ocean of light and time. Tonight, as you rest, the universe continues its silent unfolding. New stars ignite in hidden clouds. Light travels across eons to greet future eyes. Galactic dances carry on in perfect silent harmony. And somewhere, in the vast radiant sea of space and time, you float, warm, aware, and deeply connected. Thank you for journeying through the cosmos with me tonight. I hope you sleep well and dream softly among the stars. Good night.